This part, we are going to talk about how to solve collisions using two main ways: chaining, also known as bucketing, and linear probing. So, collision is inevitable. Let's try to solve it. One strategy is to store the keys in a list. These lists are known as buckets. Each bucket is actually a secondary container, an unsorted list. For example, we saw just now that the string, the key fatherhood and obstructionist maps to the same index. If you use radix 26 and we set the capital N to 100,000, all right? So what do? We cannot store both strings into the same slot, right? Unless we actually store them in a list. So we create a list there. This is actually a list in this slot, and we insert our keys there. Now, down the road, if a third key maps to the same index, I'll just append the third key to this list here. So this is what we call a bucket. It's a secondary container. It is an unsorted list. So insert can look like that. Let's take a look. This is the key to be inserted, and this is the table T. This is the table T with the size of capital N. So I perform the hash to obtain the hash value. I is the hash value. And I go to the position I in the table T and I check. If it's none, good. Empty is a gap. So I'll actually create a new list there. Otherwise, there will be a list already created there with at least one element. And then I'll append the newly inserted key to the list at that position. What about looking up? Now, this is the key, and this is the list, the table. Okay, so same thing, I actually obtain the hash code. It is in I, and I will check. The element at position I, is it none? If it's none, it's a gap, it's empty over there. The search has failed. I return none. Else, I go down the list at that position to search for the key S. I use the in operator here. Now, when you use the in operator for a list, you're actually performing sequential search. There's no other way to search for a key, right? Because this is an unsorted list. It's unsorted bucket. So this is sequential search. It should be quite obvious to you what is the problem here. Now, of course, we choose a hash algorithm which results in as few collisions as possible. And we want the hash function to spread out your keys as well spread as possible. Okay. Now, in the event that a lot of collisions happen, okay, this is just another diagram to show the buckets, and these are the keys. In the event that there are a lot of collisions, you're going to end up with a long chain, a long bucket. Okay, and this is no good. Just think about it. We have to perform sequential search. In the worst case, for example, in this bucket, I have to make 4 comparisons to search for 90. All right. Or I have to make 4 comparisons to search for something which does not exist in this bucket. Okay, so it's okay to search through a bucket where K is the length of the list at that bucket. We want to avoid that. Okay. So using buckets, right, the worst case when you perform a search on a hash table is going to be O small n. Now, what is small n? Small n is the number of elements that have been inserted into the hash table. Now, this is going to be super unlikely. This worst case won't happen. Okay, it's very unlikely. Why? This will happen only if you have 100% collision. You insert n elements, all of them go to the same slot, and it forms a bucket of length small n. Right? No, the smaller is capital N. And what's capital N? Capital N is the the array size, the table size. The smaller is capital N, the higher likelihood you are going to be nearer to the worst case because there are going to be more collisions, correct? So we're dealing with a trade-off here, speed versus space. On one hand, we do want a big N. The larger the big N is, assuming the hash function is good, the fewer collisions there will be. On the other hand, if capital N is too big, you're going to have a lot of space wastage. There'll be a lot of gaps, right? It's going to be every time you actually create an array or list, right? The program actually reserves the space for the array. Okay, so we do not want an array, a huge array with many empty slots. So where's the compromise? There's this thing called the load factor, small n over big N. Okay, remember, this is the number of elements or number of keys you want to insert into a table, and this is the size of the table. Okay, this is the load factor, and we want the load factor to be as small as possible. The smaller load factor, the less collision there will be. Okay, either we insert very few keys or we have a very large table. Okay, so with a good hash function, the average case for a lookup is going to be this. As the denominator becomes large, very much larger than the numerator, we are going to approach O1 time complexity on average. Not worst case, worst case on paper is always O small n. But I'm talking about in real life, when you actually write the code on average, time complexity should be O1 for a retrieval, for a search. If this is very much bigger than this. So it's a compromise here. Now, generally, we do not want the load factor to go above 0.5. Okay, if it goes above 0.5, what we can do is we're going to create a new table, a larger table. Okay, so let's say original table, capital N is of size 1000, we are going to double it to 2000, for example. Although 1000 and 2000 are not prime numbers, we try to choose prime numbers for the capital N. Now, doubling the table size is not as simple as it sounds because you will have to take out all the elements, all the keys, and remap them since my capital N has changed. In other words, the hash code for all the keys will be different. Okay, but this mechanism can be built into the insertion. All right, during insertion, if the load factor is above half, we can do reconstruct the whole hash table. So this will actually keep your load factor down and keep everything efficient. So let's do this in class exercise 1. So there is a hash table with capital N equals to 11, and this is the hash function, and these are the keys inserted in this order, assuming that this hash table uses bucketing or chaining. How will the hash table look like eventually? Okay, so I prepared this Excel spreadsheet. These are the keys to be inserted. All right. Let me delete this first. And this is the hash table, 11 slots. So the hash function is, let me check, 3k plus 5 mod 11, okay, equals to 3 times b3 plus 5. Okay, and I need to mod this value. Mod, comma 11. So this is the hash value for the particular key. Let me generate all the hash values first so that we don't have to bother about generation later. Okay, let's start the simulation. Okay, I'll start with key 12. Hash code is 8. I'll put 12 here. Second one, 44 goes to position 5. 13 goes to position 0. So far, so good. 88 goes to position 5. Haha, collision. So what happens? There's a bucket and there are two elements in the bucket here. 23 goes to position 8. Again, collision. 94 goes to position 1. 11 goes to position 5. Collision again. My bucket length is growing longer. 39 goes to position 1. Collision. 20 goes to position 10. 16 goes to 9. And 5 goes to 9. Collision as well. So this is the, let me centralize everything. This is the final content of the hash map or the hash table. Okay, notice that there are buckets. This is a long bucket. Okay, there are 3 elements there. In order to search for, let's say 11, I have to perform the hash function, jump to position 5, one comparison, second comparison, third comparison before I determine that 11 is there. All right. So it's going to be an OK operation where K is actually the length of this bucket. Second solution to collision is linear probing. Now, in this strategy, you want to reuse the empty spaces in the original table instead of coming up with a secondary storage. So the idea here is if a particular index is occupied, we want to try the position just beside it. Okay, so for example, let's say I want to insert element a key called 99, a key 99, and H key or H99 is actually 4. Let's assume that's the case. I jump to position 4 and I try to insert 99 there. Hey, it's occupied. So I try to insert it at position 5, occupied. I try to insert it at position 6, occupied. Position 7, occupied. Position 8, hey, it's empty. I put 99 there. So that is what this means. Now, what happens if you go to the last position? All right, let's assume that I try to insert key 100 and key 100 maps to 10. All right, so I try to insert it at position 10. It is filled. I will cycle back and insert it at position 0. So it goes backwards. And that's why we have this thing. So when do you stop? You stop when, number 1, you find a gap, you find an empty position, and you insert the key there. Okay. Second condition to stop is you cannot find an empty position, you cannot find a gap, and you come back to the original index. Now that signifies that the whole hash table is filled and there's no way you can actually insert another element. Now, usually this will not happen if you have this load factor safeguard I mentioned earlier. It means as long as the load factor is kept below a certain fraction, right? Okay, you will definitely have gaps down the road. So do you see the problem with this linear probing thing? If there are clusters of occupied slots, it becomes very difficult to insert something. You have to make many comparisons in order to insert something. In the worst case, you have to make ON comparisons, small n, where n is the number of elements already in the hash table or the list in this case. All right. Probably unlikely to happen, but it may happen. So what about deletion? Let's talk about deletion. Upon deleting a particular element at a position, you have to leave a marker so the next search will skip such cells but continue searching. What does that mean? Let's assume I want to delete uh 99, which I inserted just now. Okay, so I want to delete 99. I perform a hash. Okay. I come to position 4, it's not found. Position 5, not found. Position 6, not found. Position 7, not found. Position 8, found. I delete it. I cannot just replace the value with none. I have to leave a special marker. Just think about what will happen if you delete 99 and put a value none at position 8. There could have been a value stored here earlier. That means there could have been another insert after you have inserted 99. All right, and these values, hash code, could have mapped to something in front. When 99 got deleted, let's say there's an empty gap here. This is the empty gap because 99 got deleted. And there is a new search for this value. There will be a problem. The hash code for this value will map to, let's say, 4. And I go down the list to search for this value here. And I reach here and I see a none, a gap. I will stop my search. And I should not stop my search because, well, it was inserted after 99 earlier. So deletion is not as simple as just putting none there. You have to leave a marker. So let's assume we call this marker the defunct. Okay, this can be a special note. When we delete 99, replace it with defunct. Okay, you put a defunct note there. So that when a search happens, the search goes down the list and it sees defunct, it will carry on searching. It won't stop. On the other hand, during an insertion, when it sees defunct, it will safely insert the element there. So at any one time, a particular slot, any of these slots can have 3 states. Filled state, none state, that means empty is a gap, and a defunct state. That means, well, it's actually a gap, but if you are searching, please carry on because something got deleted there. Now let's repeat in-class exercise 2, but this time around, we assume that the hash table uses linear probing, okay, which is quite different. We'll delete this. I already have the hash codes. So let's start with the first element, position 8. Okay, this one goes to position 5. This one goes to position 0. This one goes to position 5. Collision, I will put it at position 6. Okay, this one goes to position 8. Collision, I'll put it here. This one goes to position 1. 94 goes here. This one goes to position 1. Sorry, I'm here. This one goes to position 5. Again, there's a collision. Occupied, occupied. 11 will go here. This one goes to position 1. Occupied. So I put 39 here. This one goes to position 10. 20 is here. This one goes to position 9. Occupied. 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 So 16 will end up at this point. 5 will go to position 9. Same thing. You go down the list. Occupied. 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 All the way to here. And I'll put 5 here. Okay, in this case, there's no more empty space. Like what I've said, this is unlikely to happen if you have a safeguard that the loading factor is above a certain fraction, like half, is going to recreate the whole hash table with a larger capital N. Okay, let's understand the time complexity. So on paper, the worst case for get, put, and remove for a hash table is going to be ON, where N is the number of elements inserted into the hash table, number of keys. And this is super unlikely to happen. This happens if there's a 100% collision kind of thing, but on paper, that's the worst case. Okay, regardless of whether you're using bucketing or linear probing. Now, on the other hand, the average or expected time complexity is going to be constant time. This is if you choose a good hash code, hash function, okay, and capital N, the load factor, which is small n over capital N, is small enough. We want to maintain it that way. If that's the case, your time complexity, the expected or the average time complexity is going to be likely near to O1, which is very efficient. Now, you should not use hash tables to store your key value pairs. If you need to iterate through the elements frequently, use a for loop and go through the elements for whatever reason. Okay, in that case, you might want to store it in a normal 1D list instead, or you want to sort the stored information. Okay, it doesn't help with sorting. Hash tables are useful for looking up a key to find the corresponding value, because looking up the key is almost an O1 operation. Okay, under normal circumstances, if there are very few collisions. In Python, when you use a dictionary, it is a hash table. We have seen how to, I believe you have used Python dictionaries before. This is how you actually insert a key value pair. This is how you actually do a lookup. And this is how you check if a particular key is in the dictionary. Now, this in operator, when used on a dictionary, is likely to be near to O1. If the in operator is used on a normal 1D list, it's going to be a sequential search. It's going to be ON worst case. You may not have seen how efficient it is to look up or retrieve an element, a value using a key when you use a dictionary, because the amount of data used is very small. You can do an experiment to find out if there is a time difference when you actually try to search for something, a hash table, a dictionary which has 1,000 elements versus search for something from a hash table which has only 10 elements. Shouldn't be 10 versus 1,000. Let's make it bigger, 10 versus 1 million, for example. Okay, and you will see that the amount of time required should not differ too much. Okay. This is a summary. Read this yourself.